We'll look at one last example of taking this process from start to finish with an applied problem. Here we have Fernando who builds bird baths and bird houses. He can make a total of 7 per day. A bird bath costs $8 to make while a birdhouse costs $6 to make. He has $48 to spend on materials, and when he sells them he makes $12 in profit. On a bird bath, $9 in profit on a birdhouse. We want to determine how many he should make of each type to maximize his profit. Meaning our objective function is to maximize $12 times each bird bath plus $9 times each birdhouse. We know that he can make a total of 7, so x plus y, the number of each that he makes, can't exceed 7. And we know how much it costs to build each type and how much money he has available. Meaning that $8 times x, so $8 per bird bath plus $6 per birdhouse has to be less than or equal to $48. And the two implied statements that x has to be greater than or equal to 0 and y needs to be greater than or equal to 0. Gives us our system of inequalities that we can graph to determine our feasible region. Flipping over to Desmos, we can graph our system. Using that method with the curly braces to nail down our shaded region. And we can identify our points of intersection at 0, 7, 3, 4, 6, 0, and the origin 0, 0. We can go ahead and set up our table to optimize that objective function, which in this case would be 12x1 plus 9y1. Plugging in our pairs, we get 0, 0, 0, 7, 3, 4, and 6, 0. In this case, again, like we had in the last example, we get two different possibilities, two different types of production that yield a maximum profit of $72. We can plot these points, which we skipped over, at 0, 0, 0, 7, 3, 4, and 6, 0. To establish that feasible region. And what we found from testing those corner points is that in this case there are two possibilities. He can either make 3 bird baths and 4 bird houses, or just make 6 bird baths to earn a maximum profit of $72. Ideas to keep in mind here as you're working through these problems is that, again, there's no specific pattern to which of our points of intersection, which of those corner points will be the value that optimizes the function. We always have to test all of them. Then what we're looking for is either the maximum or minimum value in our table. Oftentimes, I would say most often, we'll only end up with a single pair that gives us that optimized value for our objective function, our objective expression. But in a case where we have a pair, then we would have two different possibilities that yield that same optimal scenario.